So I've decided to do the second lecture today on enthalpy. It's a shorter lecture and it relates a lot to the previous lecture I just posted. But so for lecture 36, we're going to be talking about another way of calculating reaction enthalpies, and we're going to be doing that by breaking and forming bonds. So the way we did it last time, if you'll remember, is we did it a few different ways. We did it by pretending we were taking alternate routes through our reaction. So instead of measuring the reaction directly, we just pretended it was two other reactions. We also calculated reaction enthalpies from enthalpies of formation for different reactions. Today, or this time, I'm going to talk about how we can calculate delta H's of reactions from the breaking and forming of bonds. So the way we're going to do this is we're going to break all the bonds in our reactants, then we're going to form all the bonds in the products, and then we're going to find the difference in energy here. So basically what we're going to do is we're going to find our delta H of our reaction by summing up the delta H of all the bonds we broke, and then we're going to subtract the sum of the delta H of all the bonds we formed. So what that means practically is that we're going to look at our reactants and our equations, determine which bonds are broken, and determine the energies of those bonds. So bond enthalpies are very similar to bond energies, and for the sake of this class, we're going to say that they're the exact same thing. So when we describe a bond enthalpy, we're talking about the energy required to break 1 mole of a certain type of bond. And we're going to talk specifically in the gas phase. So this method that I'm talking about today is not as good as the other two methods that we talked about in the last lecture, but it's useful for approximation. So our bond enthalpies then are a measure of bond strength, and larger bond enthalpies, of course, mean stronger bonds. So if we look at our table here of different bonds, these tables, or a table like this can just be found in your book, but of course the higher the bond order we have, the stronger the bond we have. So a carbon-carbon single bond has a strength or a bond enthalpy of 348 kilojoules per mole. The double bond, of course, has nearly double that strength. It has a bond strength of 614 kilojoules per mole. Something to remember that should be helpful is bond enthalpies are always positive. So when you're breaking a bond, it always requires that you put energy into the system to break a bond. And it always, whenever a bond is formed, you're always releasing energy. Which means that the signs of bond formation are always the same and bond breaking are always the same, whether positive or negative in terms of energy. Now the reason this method is less good than the methods we talked about during the last lecture are that these bond energies for, say, a carbon-carbon bond is just the average bond energy found from breaking a bunch of different carbon-carbon bonds in a bunch of different molecules. In reality, the bond strength depends on what molecule you're in, what else these carbon atoms are bonded to, whether they're bonded to or double bonded to an oxygen or bonded to a nitrogen, etc. All that's going to affect this bond strength. And so because of that, the calculations we do in this lecture are only going to be approximate, but they're useful when you don't have the delta H of formation of a specific species in a chemical reaction. So let's look at how we'd actually work a problem by breaking and forming bonds. Let's say we're reacting methane gas, so CH4, with oxygen gas, which is O2, and we're forming CO2 and water. So in this reaction, we're starting with CH4. CH4 has 4 carbon-hydrogen bonds. We're going to have to break all 4 of those bonds. And we're going to look up in our table to find that a CH bond has a strength of 413 kilojoules. And we're going to multiply that by 4 because of the 4 bonds. We're also going to have to break the bonds between the different oxygen atoms in the oxygen molecules. This is an oxygen-oxygen double bond. And that oxygen-oxygen double bond has a strength of 498 kilojoules. We're going to multiply that by 2, not because there is a double bond here, but because there are 2 molecules here. So when you're looking up this energy, you would look up the energy specifically for the double bond species. For this case, we'd be looking up the energy for the oxygen-oxygen double bond. We're going to break those both simultaneously, and that'll have an energy of 498 kilojoules. Okay. So we're going to multiply this number out, multiply this one out, add those together, and we're going to find that we have to put in 2,648 kilojoules of energy to break all of these bonds in our reactants. Okay, we're then going to take all these atoms now that we've separated out, we're going to recombine them into new molecules. So we're going to be forming some bonds. And as we form bonds, we're going to be releasing energy from our system. So let's start with the CO2 down here, right? We're going to form carbon dioxide, and that'll have carbon double bonded with oxygen twice. So we'll have to look up the energy for the carbon-oxygen double bond in the table. It is 799 kilojoules. We have to put a negative sign in front of this because this is bond formation. Bond formation gives off energy, and so that gives us a negative sign. And so we're going to have to multiply this by 2, of course, because we're forming 2 of these double bonds. And then over here, we're going to have to form the oxygen-hydrogen bonds. Oxygen and hydrogen have a bond energy of 463 kilojoules. Again, we're throwing the negative sign in because we're forming bonds. We have to multiply this by 4 because we have 1, 2 bonds in each molecule, and we're forming 2 molecules in this reaction, or 2 moles of water. So we're going to have to multiply that by 4. We're going to multiply these numbers out and add them together to find that this gives us 3,450 kilojoules of energy being released. So we're going to take this 2,000 kilojoules that we put into the system, add it to this 3,000 we released, and find that the overall delta H of this reaction is negative 802 kilojoules. So that's just this value added to this one. Let me know, of course, if you have any questions or concerns about that. So let's give it a little bit of practice, and let's estimate the energy of this reaction. Okay, we have hydrogen, or H2 plus Cl2 going to 2HCl. So in this, we'll be breaking 1 mole of hydrogen-hydrogen bonds, breaking 1 mole of chlorine-chlorine bonds, and forming 2 moles of HCl bonds. So of course, we need to look up the energies of all of these bonds in a table. The hydrogen-hydrogen bond has an energy of 436 kilojoules per mole. Chlorine and chlorine has an energy of 242 kilojoules per mole. And HCl has an energy of 431 kilojoules per mole. So let's break 1 mole of hydrogen-hydrogen and chlorine-chlorine bonds. So the hydrogen-hydrogen bond again has an energy of 436 kilojoules. The chlorine-chlorine has an energy of 242 kilojoules. Add those up to say that we need to put in 678 kilojoules of energy to break everything on the left side of this reaction. Now let's make 2 moles of our HCl bonds. So that's going to be 2 times this bond energy of 431. We put that negative sign in there again because we're forming these bonds, and when you form bonds, you give off energy. So that's a negative energy for the system. That means we're giving off negative 800, or we're giving off 862 kilojoules of energy. We add those 2 numbers together to find that the overall delta H of this reaction is negative 184 kilojoules. So the way I'm doing it is I'm just converting these bonds being formed into a negative number. Another way of thinking of it is how it's written out in this equation, where we sum up the bonds that are broken. You can sum up the bonds that are formed and find the difference. For me, I like to just change all the bonds being formed into a negative number and leave all the bonds being broken as positive numbers. Either way works out. Again, I'm going to drive home this point that these calculations using this process are only an approximation because the tabulated bond energies in your table are just averages from a bunch of different molecules. This approach works best for gas phase reactions because when you have a reaction occurring in solvent, so if let's say you have stuff dissolved in water or methanol, the dipoles or hydrogen bonds in water and methanol are going to interact with your products and reactants, and they're going to change some of the energetics there. And I'm going to emphasize again that this is most useful when you don't have the delta H of formation for something in your chemical reaction. And that actually happens quite often when you consider all the different ways you can arrange carbon, hydrogen, oxygen, nitrogen, fluorine, and everything else on the periodic table into different molecules. You find out pretty quickly that there's a lot of different molecules. And so measuring the delta H of formation for each of those is pretty labor intensive. There's actually a guy at University of Utah that does that all the time. That's his whole research group. He's a pretty nice guy. Anyways, let's get into some practice here. So just using the data provided, estimate the enthalpy of this reaction. Now go ahead and pause that if you want right now and try and work that out. But if we look at this, we have CH4 reacting with I2 going to CH3I plus HI. So we're actually only breaking one carbon hydrogen bond here and one iodine bond. We're forming one carbon iodine bond here and one hydrogen iodine bond, or iodine, whatever. So we're going to just multiply, or we're going to find the energy of the carbon hydrogen bond here, which is 413 kilojoules per mole. We're going to multiply that by 1 mole because there's a 1 in front of that. Then we're going to break 1 mole of I2 bonds. So we find the energy for that. We take 151 times 1 mole. Then we take, or we're forming 1 carbon iodine bond here. We take the energy for that, it's 240. We multiply it by 1 mole. We give it a negative number because it is a product. And it's a bond being formed. And then of course we take the bond energy of hydrogen or iodide, multiply that by the 1 mole in front of hydrogen iodide, give it a negative sign because it's a product. Then we just work out all that math, and we find that it's 25 kilojoules per mole. All right, so let's really quickly just review what we've done now with Hess's law. I've given you 3 different ways to find the delta H of a reaction. The first is to sum up the delta H's of other reactions, either adding them or subtracting them, until you find a combination of other reactions that gives you your original reaction. The second way we talked about was summing up the delta H of formation for your products and subtracting the sum of the delta H of formations for your reactants. And then the way we talked about today was summing up the delta H of your bonds being broken and subtract the sum of the delta H of the bonds being formed. Now, a quick note here. In this second method, we have products minus reactants. But in this third method, we actually have reactants minus products. Make sure you have that straight in your mind, which ones, or which way you do these reactions. If you can think through it logically and remember that forming bonds releases energy, breaking bonds requires energy, you can usually figure this out. But if you feel like you're not going to be able to remember that logic, then just remember that for summing the formation enthalpies, you're doing products minus reactants. If you're breaking and forming bonds, you're doing reactants minus products. Okay, a question like this, or a question that you could see could look like this. Using the data provided, estimate the enthalpy of the following reaction. And this is going to lead into a practical application of all of this. And so here we have CH4 reacting with oxygen to form CO2 and H2O. I'll let you go ahead and pause the video now if you want to work through that. Okay, so all we're going to do, we got to look at our table here and find that this is listing delta H of formations. So for delta H of formations, we're going to be taking the products minus the reactants. So we're going to take the delta H of formation for water and CO2. We're going to multiply those by the coefficient in front of these. So for CO2, we've got a 1 in front of CO2. So that's 1 mole of CO2 times the delta H of formation for CO2, which is negative 139.5. We have the delta H of formation of water, we have the coefficient for water, which is 2, multiplied by the delta H of formation, which is negative 241.8. And then we're going to have to subtract the delta H of formation of our reactants. So we'll start with CH4. We got a 1 in front of that. So 1 times negative 74.8. And then, of course, the delta H of formation for O2 is going to be 0 because it's a pure element in its standard state. We work out all that math, and we find that burning CH4 gives off 802.3 kilojoules of energy per mole. Really quickly, this question is very similar. The only difference is that now we're burning propane instead of methane, so that's going to react with more oxygen and it's going to form more CO2 and water. I'm going to run through the calculations on this one fairly quickly. But here we have 3 moles of CO2 times negative 393.5. We have 4 moles of water times negative 241.8. So that's all right here in our equation. And we have 1 mole of propane, C3H8. So we're going to have a negative here because it's a reactant. We're going to times that by negative 103.8. We'll work all that math out and find that when we burn propane, we actually use up we actually release 2,000 kilojoules of energy per mole of propane that we burn. So those two questions are very similar, and so the question I offer you now is, which is more efficient, burning methane or burning propane? Well, it actually depends how you define it. If we're talking about per mole, propane gives off way more energy per mole than methane. But in real life, we don't sell things by the mole, almost never. If you're a chemist, you buy a lot of things by the mole, but nobody else really does. We usually sell it by mass or by volume. So we need to figure out by mass which of these is more efficient. So for CH4, it's letting off 802 kilojoules of energy for every 16 grams, which means it gives off 50 kilojoules of energy per gram. But for the propane, we take that 2,000 kilojoules per mole, divide it by the molecular weight of propane, which is 44. Then propane actually only gives off 46.35 kilojoules of energy per gram. So when we talk about fuel value, which is measured in energy per gram, methane actually has a higher fuel value than propane. There's another metric for measuring fuels called fuel density, which is energy per volume. And so in energy per volume, propane is actually higher in energy than methane. And if we look at all the basic hydrocarbons, just long chain hydrocarbons, I have them listed here on the bottom. So methane, ethane, propane, butane, pentane, etc. So these are just long carbon chains. You'll see that the fuel value actually goes down as the chain gets longer. The reason the fuel goes down is because with methane, you have a hydrogen to carbon ratio of 4:1, but as you increase the number of carbons on that chain, the ratio of hydrogen to carbon gets really close to 2:1. And if we compare the energy efficiency of hydrogen reacting to carbon, see that 2 grams of hydrogen to make H2O releases 241.8 kilojoules of energy. But when we take 12 grams of carbon to make CO2, we give off 393 kilojoules of energy. So this is just hydrogen gas and elemental carbon that we're comparing here. And so if you compare that, carbon, you're using 6 times the mass of carbon to produce only about 60% more energy. And what that means is when comparing which produces more energy in fuels, hydrogen or carbon, hydrogen gives off about 3 times as much energy as carbon when we're dealing with weight. Or more specifically, sorry, hydrogen gas gives off about 3 times more energy than methane gas when we're comparing gram to gram. I'll give you one more application of bond breaking and formation providing energy. So most of the energy in your body is provided or stored or transported, depending on which function you're talking about, by this guy called ATP. That stands for adenosine triphosphate. And this guy breaks down to adenosine diphosphate. Now that means that you actually have to do some bond breaking right here between this second and third phosphate to get rid of that last phosphate group to go down to the adenosine diphosphate. And we said that it always requires energy being put in to break a bond, but this bond breaking actually provides all the energy for your body. So how does bond breaking release energy? Well, as this bond breaks, you actually form a whole bunch of other bonds, and the formation of those other bonds actually provides net energy out into your body to keep you warm. If you go on to biochemistry, you'll get to learn all about ATP and ADP. You'll have to learn a whole lot more about it than I just taught you. Anyways, hope this lecture was helpful. If you have any questions or concerns, feel free to reach out, and good luck on the exam. And since you probably are watching this after the exam, I hope you did well on the exam. And we'll see you next time.